For decades, aviation followed a simple rule. If you wanted to fly faster, higher, or farther, you had to build stronger, heavier, and more complex machines. Progress came through brute force. More metal, more power, more fuel. It was slow, expensive, and risky. But one engineering decision changed that mindset forever. Not a flashy invention, not a new engine. A shortcut, quiet, controversial, and at first, deeply unpopular. And once it worked, aviation was never the same again. In the early days of jet travel, engineers were obsessed with strength. Aircraft were built like flying fortresses. Thick wings, heavy frames, and layers of redundancy stacked on top of redundancy. The philosophy was simple. If something could fail, build around it with more hardware. That approach kept planes safe, but it came at a cost. Aircraft were heavy, fuel-hungry, and limited in range. Every added kilogram reduced efficiency. Every extra system added maintenance headaches. Airlines accepted it because there was no alternative, or so they thought. Then came the problem that forced engineers to rethink everything: speed. As jets pushed closer to the speed of sound, aircraft started behaving in ways no one had seen before. Wings flexed more than expected. Control forces changed mid-flight. Pilots described aircraft that felt stable one moment, unpredictable the next. Traditional solutions, thicker wings and stronger structures, only made the problem worse. Heavier wings created more drag. More drag demanded more thrust. More thrust burned more fuel. The cycle was becoming unsustainable. Some engineers began asking a dangerous question. What if we stopped fighting physics and instead worked with it? The answer didn't come from adding strength, but from removing it. The shortcut was flexibility. Instead of designing wings to resist bending, engineers allowed them to bend on purpose. Instead of overbuilding structures to handle every extreme scenario, they calculated exactly how much stress a component would experience and designed only for that. No more just-in-case metal. No more unnecessary weight. This was radical thinking. At the time, many believed flexible structures were unsafe. To older engineers, a wing that visibly bent in flight felt wrong, like watching a bridge sway under traffic. It went against everything aviation had been built on. But the math said otherwise. By allowing controlled flexibility, wings could absorb loads instead of transferring them violently through the airframe. Stress was spread out, not concentrated. Aircraft became lighter without becoming weaker. In fact, they became more predictable. The problem wasn't strength. The problem was stiffness. This shift didn't happen overnight. Early designs faced intense scrutiny. Test pilots were uneasy. Regulators demanded proof. Airlines worried about public perception. Passengers didn't want to look out the window and see wings curving upward. Yet flight after flight, the results were undeniable. Flexible wings reduced structural fatigue. They improved aerodynamic efficiency. They allowed aircraft to fly farther on less fuel. And perhaps most importantly, they opened the door to designs that were previously impossible. Once engineers accepted flexibility, other shortcuts followed. Flight control systems no longer needed to rely purely on mechanical linkages. Computers could manage stability more precisely than human hands ever could. Instead of designing aircraft that were naturally stable but inefficient, engineers built aircraft that were aerodynamically unstable, but digitally controlled. This was another controversial leap. Why would anyone design a plane that needed computers to stay in the air? Because it worked. By relaxing natural stability requirements, designers gained freedom. Aircraft could be lighter, faster, and more responsive. Computers made constant micro-adjustments, correcting movements before pilots even felt them. What once required heavy mechanical systems could now be done with software. It was an engineering shortcut in the truest sense, not cutting corners, but cutting weight, complexity, and limitations. The impact spread quickly. Military aircraft adopted the concept first, where performance mattered more than tradition. Then commercial aviation followed, cautiously at first, then fully. Long-range flights became cheaper. Aircraft maintenance intervals grew longer. Fuel efficiency improved across entire fleets. Passengers never noticed the shortcut directly. They just experienced quieter cabins, smoother rides, and cheaper tickets. But behind the scenes, aviation had crossed a line. The industry no longer relied on brute strength alone. It trusted calculation, flexibility, and controlled risk. Engineers stopped asking, "How strong can we make it?" and started asking, "How smart can we design it?" And that mindset didn't just change aircraft. It changed how aviation thought about safety, efficiency, and progress itself. Because once you accept that sometimes less structure can be safer than more, there's no going back. Once aviation crossed that line, there was no turning back. The shortcut, flexibility, precise engineering, and computer-managed control quietly became the foundation of modern flight. But it didn't arrive without consequences, and not all of them were obvious at first. As aircraft grew lighter and more efficient, systems became more interdependent. A wing was no longer just a wing. It was part of a carefully balanced equation involving software, sensors, and control laws running thousands of calculations per second. The margin for error shrank, not because planes were weaker, but because everything was optimized so tightly. In the past, excess metal acted like a buffer. If something behaved unexpectedly, the structure often absorbed the mistake. Now there was less room for sloppiness. Every assumption had to be correct. Every calculation had to be right. And most of the time it was. Modern aircraft proved astonishingly reliable. Flexible wings handled turbulence better than rigid ones ever could. Fly-by-wire systems reduced pilot workload and prevented countless accidents before they could even begin. Fuel savings reshaped airline economics, opening routes that once made no financial sense. The shortcut worked, but it also shifted where risk lived. Instead of being visible, cracks, fatigue, physical wear, it moved into software, logic, and system design. Problems became harder to see, harder to explain, and sometimes harder to fix. When something went wrong, it wasn't always obvious why. This forced aviation to evolve again. Training changed. Pilots were no longer just flying the aircraft. They were managing systems. Engineers had to think not just like designers, but like psychologists, anticipating how humans would interact with automated decisions under pressure. Regulators adapted too. Certification wasn't just about stress tests and wind tunnels anymore. It was about simulations, edge cases, and scenarios that might only occur once in a billion flight hours. Every layer of progress added another layer of responsibility. Yet despite the challenges, the industry didn't retreat because the benefits were too great. Without this shortcut, modern aviation simply wouldn't exist as we know it. Ultra-long-haul flights, composite airframes, aircraft that quietly flex, adapt, and respond to conditions in real time. All of it traces back to that original decision to stop overbuilding and start trusting precision. Even today, when you look out a window and see a wing bending upward during turbulence, you're witnessing that philosophy in action. That curve isn't a flaw. It's the aircraft doing exactly what it was designed to do, absorbing energy, protecting the structure, and keeping the flight smooth. It's engineering humility made visible. The realization that strength doesn't always mean stiffness. That safety isn't about excess, it's about understanding. And that sometimes, the most revolutionary breakthroughs don't come from adding more, but from daring to remove what you thought you needed. This shortcut didn't just change how planes were built. It changed how engineers think. Across industries, from bridges to spacecraft to renewable energy, the same lesson appears again and again. Optimize instead of overbuild. Model instead of guess. Trust physics but respect complexity. Aviation learned it early, and the skies are quieter, safer, and more accessible because of it. So the next time you fly, remember this. You're not being carried by brute force. You're being carried by a carefully calculated balance of flexibility, control, and trust, born from a single decision to take a different path. A shortcut that reshaped the sky. If stories like this, hidden engineering decisions, quiet turning points, and the unseen forces behind modern technology are what keep you watching, then make sure you stay connected. Subscribe to the channel, share this video with someone who loves aviation or engineering, and let me know in the comments which moment in aviation history you think changed everything. Because the most powerful revolutions are often the ones no one notices until they're already flying inside them.